Today I've got a pretty exciting video which is a little bit more off the cuff than normal. I generally want to explain what the universal enveloping algebra is, and mostly because I think it's a really cool object, and not only is it a cool object in mathematics, but it has a very cool name. Universal enveloping algebra just has a really nice ring to it. Now, in order to properly explain this object, we need to recall some things that we've done in previous videos. And some of this is quite technical, but we've got what I think are really good, simple explanations of this background information in previous videos. That being said, we're going to review it a little bit. So let's recall what a Lie algebra is. So G is a Lie algebra, and I'll use this fancy G to be the Lie algebra. So this is like a /mathfrak G if you speak LaTeX. And generally we use this fancy G because this is the Lie algebra associated to capital G, which is a Lie group. So like I said, I've done several videos on the channel about Lie algebras. One where we explicitly describe why SL2, the Lie algebra, is related to the Lie group SL2, and another about the cross product, and I think one more about something else. Maybe those should be linked like somewhere up there right now. Okay, so let's recall the axioms of a Lie algebra. So first of all, it needs to be a vector space over a field. Maybe we'll just use our ground field as the complex numbers just to keep it simple. We really need it to be the complex numbers, or we'd like it to be the complex numbers, because that ground field being algebraically closed makes it kind of nice. So that's what we start with. We need something called a vector space. And then we also need some sort of multiplication. And that multiplication is called the Lie bracket, and it's denoted like this. So those are the places where you put the objects. So you put an element from the Lie algebra here and an element from the Lie algebra here. And in fact, what it does is it's bilinear, and it goes from G cross G to G. So in other words, if you have X and Y are in your Lie algebra G, then bracket XY is a potentially new element from your Lie algebra G. And then this bracket has to satisfy some rules, obviously. And so maybe the first rule is that it's bilinear. I won't write that down. That means you can split it up with scalar multiplication and vector addition. Another thing is it is skew symmetric, and that means that if you do bracket XY, you get negative bracket YX. So it's not commutative, it's like anti-commutative. And then maybe the most important thing is it satisfies something called the Jacobi identity, and that involves the non-associativity of this Lie bracket. So we have X, Y, Z, so let's write it like that. So bracket X, bracket Y, Z, plus, let's see if we can get this right, Z, X, Y, plus, let's see, the next one would be Y, ZX equals 0. So that's the last rule. And like I said, we've looked at several examples of nice Lie algebras on the channel before. Maybe one that I'd like to recall real quick, or maybe we'll recall a couple of them real quick. So let's do the cross product. So this is the cross product. So you learn in a multivariable calculus class, or maybe an analytic geometry class, or a linear algebra class or something, about the cross product. And the cross product is a non-associative map, but in fact the Jacobi identity holds. Furthermore, it's skew symmetric and it's bilinear. So the cross product, and here we need this to be over C3 or R3. Okay, so that's one example. Another thing that you could take is the set of n by n matrices with entries in C, and then you could define your bracket AB to be AB minus BA. So that's another example that we've seen. And then a special case of this would be the Lie algebra SL2, which is made up of the following 2x2 matrices, or you can think also about this as just being abstractly defined by H, which is this diagonal matrix, 1, 0, 0, negative 1, E, which is 0, 1, 0, 0, and F, which is 0, 0, 1, 0. And here the important thing about this, and I'll recall the commutation relations between E, H, and F in this case, because they'll be important for an example that we will do later. And that is if we have the bracket of H with E, we get 2E. And you can check these just with calculation. We're using the same commutator that we have up here for our matrix algebra. And then if we do H with F, we get negative 2F. And finally, if we do E with F, we get H. So those are the defining relations for the elements of SL2C. Okay, so let's see. We've got one example right here, another example, and another example. And then we have one more that we've done a couple of videos on, and that is the so-called Witt algebra. And let's recall that the Witt algebra was made up of these operators Ln, and this was infinite dimensional. These were indexed over the integers, and this Ln could be represented by some differential operator on a polynomial ring, or maybe a ring of Laurent polynomials. And that differential operator looked something like this: z to the n minus 1, and then the partial with respect to z. So like I said, that's an operator. That's actually a really important takeaway. The fact that the vectors inside of this Witt algebra are themselves operators on another space. This is actually like getting to the theme, which happens a lot in algebra, and that is studying an object by its action on another space instead of, kind of its inherent structure. And that's called representation theory. I thought I'd make a simple video about that in the future. Maybe post in the comments if you'd like to see that video. Also, it helps with engagement when I say stuff like that. Okay, so this is the first thing that I'd like to recall, this notion of a Lie algebra, which we've breezed through quickly, but you can check out previous videos if you'd like to. Now I'm going to look at one other thing that we've recalled that looks quite a bit different, but then we're going to smash these two ideas together. So next up, we will quickly recall the tensor product of vector spaces. So let's say we've got V and W, and these are both vector spaces over a common field. I'll take C to be my ground field again, just because we're generally going to be working over C in this video at least. And then let's recall that V tensor W was equal to the span of V tensor W. So this is like the tensor product of the vector space V with W. And this is like a component of what's building the parts of V tensor W. So little v tensor little w, where little v comes from V and little w comes from W. And I've done some videos on the tensor product on this channel as well. Those should be linked above. Okay, and then let's recall that these satisfy some rules, and they're really the rules that we would like them to satisfy. And that is, if we were to take alpha v tensor w, so in other words, we do the scalar multiplication with alpha. Let's say that alpha is a complex number. I won't write that down, I'll just say it. Alpha is a complex number. Then we can pull that out. So we have alpha and then V tensor W. Then likewise, if we have V tensor alpha times W, we can pull that out as well. So we have this is alpha and then V tensor W. So to start with, we have these two rules about how the tensor product acts. But we've got this word product within the tensor product, and so perhaps it should satisfy some more rules that a product satisfies. And in fact, when we did our construction, we forced it to satisfy a couple of more rules that look like a distributive property. So also we have the following rule. So we have v tensor w1 plus w2, where that's the sum of two vectors in w, is equal to v tensor w1 plus v tensor w2. So in other words, this tensor product multiplies over. That's not great terminology, but it distributes over the addition. And it distributes over the addition in the other component as well. So if we have v1 plus v2, tensor product with w, then that's going to be the same thing as v1 tensor product with w plus v2 tensor product with w. Okay, great. So let's look at maybe a quick example. So let's say we have this. Let's say v is equal to c2. So that's going to be everything of this form. Maybe we'll say alpha, beta, where alpha and beta are complex numbers. So those are two vectors. And then we have w is c3. So that's going to be everything of the form a, b, c, where a, b, and c are complex numbers. So that's going to be three vectors. So what does an arbitrary element of the tensor w look like in this case? Well, let's just write down a couple so that we have a feel for what's going on. So elements of the tensor w. So here's one element. We could have 2, 1, tensor product with 0, 1, 3. So that would be one of them. Notice that by one of these rules over here, that's going to be the same thing as 1, 1/2 tensor producted with 0, 2, 6. So we took a multiple of 2 from here and we moved it over to the other tensor factor. That's totally allowed in this case. Other things that we could do is we could expand this in terms of the basis vectors. I won't expand it all the way out in terms of the basis vectors, but maybe a little bit. So this is going to be the same thing as 2, 0 plus 0, 1 tensored with 0, 1, 3. And then from there, we could maybe write this as 2, 0 tensored with 0, 1, 3, and then plus 0, 1 tensored with 0, 1, 3. So something like that, if you will. And you might start to look at this and think that, oh, this looks like it could be pretty similar to some rectangular matrices of a certain size. And in fact, we have that in this case. What we have is this tensor product of v with w is essentially the same thing as 2x3 matrices with entries in C. So something like that. And you might say, well, exactly how does this work? Well, I think there's probably a bunch of ways that you can write down this map, but we would maybe identify the vector alpha beta tensor A, B, C with something like this. So we need two rows and 3 columns. So maybe something like alpha A, alpha B, alpha C, and then beta A, beta B, and beta C. See, we did that like little multiplication there. So that would be like a map that describes M2x3 with this V tensor W. Okay, so I think that's a pretty good review of both Lie algebras and this tensor product. Obviously, this is not enough to get a good idea of exactly what's going on, but like I said, I've made some previous videos of this that you should most definitely check out. Now I want to smash these two ideas together into something called the universal enveloping algebra. All right, now we're ready to do it. So the universal enveloping algebra, so this is something that's associated to a Lie algebra. So what we'll want to do is start with some Lie algebra G. And I'll do this in general, and then maybe we'll look at our favorite example with SL2. And there are a couple of steps that we have to do here. The first thing that we'll do is form something called the tensor algebra. And I did a previous video where we looked at how to make polynomials out of the tensor product. And so this is kind of related to what we did there. So what's the tensor algebra? Well, it's going to be quite big. So we'll call it TG, and it'll be equal to complex numbers direct summed with G, direct sum with G tensor with itself, and then direct sum with 3 copies of G tensored to itself, and so on and so forth. So, in fact, you can think about this as like your constants. These are your terms that are linear in G, because G is just by itself. These are terms that are quadratic in G. You can think about this as like an element from G times an element from G. The next ones would be cubic, and so on and so forth. Now, I'd like to introduce a little bit of notation that will help us out here. And that is when we take a tensor product of something with itself, we have some notation, and that would be this tensor power. So it'll be G upper tensor 2 in this case. The next one would be G upper tensor 3, and so on and so forth. So we could shorten this as follows. This could be the direct sum from n equals 0 to infinity of the n-fold tensor product of G, where we take the 0-fold tensor power to be just the complex numbers themselves. Okay, so that's our first thing, is to create this tensor algebra. But then somehow we would like to encode that bracket that's part of the Lie algebra into the structure of this tensor algebra. And the way to do that, using kind of what I'll call universal algebraic constructions, is via a quotient. So what we'll do, and this is like the last step to creating this universal enveloping algebra, is we'll call U of G equal to T of V quotiented out with an ideal of elements of the following form. So we'll take X tensor Y minus Y tensor X, and then minus the Lie bracket of X with Y. So it's generated by things of this form. Now let's recall that if we're putting something in the ideal that we're forming the quotient from, that means that this object in the ideal is 0 in the quotient. So let's maybe put that as a little bit of a summary over here. So in U of G, what we have is that X tensor Y minus Y tensor X is in fact equal to bracket XY. So this actually provides some motivation for why in physics class you might always write this bracket XY as this kind of difference with the product happening in a different order. So technically, from a mathematical standpoint, this bracket XY is just a Lie bracket. It could be the cross product, which has nothing to do with something like this. But when you're pushing towards this thing called the universal enveloping algebra, then you equate this Lie bracket with this commutative product, or this really not commutative product, but measurement of how the product is not commutative. Okay, and then I'd like to point out that often in this case, we do a little bit of simplification. And that simplification is just to leave out the tensor. And so we would often write xy minus yx equals bracket xy like that, where we just think that xy is really x tensor y, just to keep the notation a little bit simpler. Okay, so let's look at an example. So let's investigate the universal enveloping algebra of SL2. So just recall that this is going to be the tensor algebra of SL2, where we make this tensor product have the following like commutation relations, if you will. But the important thing to do is that this looks mostly like polynomials. In fact, at the level of the tensor algebra, this looks like polynomials where we have no rules for the commutativity. But down at the universal enveloping algebra, this in fact looks like polynomials where the commutativity is governed by the bracket from the Lie algebra. So let's maybe write that right here. So you can really think about this as polynomials in well, let's write it like this, HEF, where recall that those were our basis vectors for SL2, with HE minus EH equals 2E, because remember that's supposed to equal bracket HE, but bracket HE in the Lie algebra was 2E from what we saw before. And then likewise, HF minus FH is equal to negative 2F. And then EF minus FE is equal to H. So in other words, we have a polynomial in 3 variables. Those 3 variables are H, E, F. But that polynomial algebra is not commutative. It's a little bit of a misnomer to call it a polynomial algebra. It's in fact a universal enveloping algebra. So this space is not commutative, but it has a lack of commutativity defined by the bracket relations from SL2 itself. Okay, so let's look at an example of an element within USL2, the universal enveloping algebra of SL2. So we could have something like this, E squared H E F. So that's most definitely an element from USL2. And why is that? Well, that's a monomial in this universal enveloping algebra. But, you know, it's a little bit of a bummer that we've got E's here and we have E's here. So maybe we should impose some sort of alphabetical order. Maybe the alphabetical order should be all of the H's move to the left, all of the E's are in the middle, and all of the F's move to the right. But that means that this E and this F are in the correct order, whereas this H is out of order because it comes to the right of these 2 E's. So let's see if we can fix it. So I'm going to write this as E, E, H, E, F, just expanding that E squared. Okay, and now let's move into this EH and notice that this EH is the same thing as HE plus the bracket of E with H. So I think we could agree with that. And why is that? That's because if you were to subtract this HE over to the other side, you would get the bracket of E with H. So let's maybe make sure to be really sure about that. That's because bracket EH is equal to EH minus HE by what's going on in our universal enveloping algebra. But we can do some simplification on this because we have some rules for commutativity. In fact, EH is equal to negative HE by the skew symmetry, but HE is equal to 2E. So this is equal to negative 2E. So let's see, we can take this entire thing right here, EH, and we'll replace it with HE minus 2E. So let's do that. So I'm taking this right here, and I'm going to write this as E, and then I'll put a red box where we're making this commutation relation, and I'll write this as HE minus 2E, and then we'll have EF. Okay, so that's where we are so far, but that's getting a bit messy, so let's move our calculation up here. So this is where we left ourselves off. We took our original monomial, E squared HEF, and we rewrote it in this format. And that came from using our commutation relations to put one of these EH's in the correct order, like we did over there. So it was this EH, which was expanded by the E squared H. But now we know by the construction of the tensor product that we have a distributive rule and all of that kind of stuff. So we might as well rewrite this as EH E squared F. So that's from this E left multiplying here, and this EF right multiplying here, and then this is going to be minus 2 E cubed F. Here we have E, E, E. And now notice this one is in the agreed upon order. We have E's to the left, F's to the right. There are no H's. We had decided that the H's should be all the way to the left. But this one is not in the right order. That's because we still have this EH right here. So we have to fix this the same way that we did before. But let's recall that that will be HE and then plus bracket EH. But we already determined that bracket EH was minus 2E, so let's write this as minus 2E. Okay, that's good. So now let's rewrite this. So we have this EH, we'll write that as HE minus 2E, and then this is times E squared F from this term, and then we'll have minus 2E cubed F. Okay, so this is really starting to shape up quite nicely. Let's see what happens when we were to write this all out. So we'll end up with HE cubed F minus 2E cubed F minus another 2E cubed F. So that'll be minus 4E cubed F. Now we've got it in our correct order. And what I'd like to point out here is that the degree is not maintained during this calculation. So unlike what's going on in a polynomial ring where the degree of a polynomial is canonical, in other words, you can write it any way you want and you get the same degree, the degree of an element in a universal enveloping algebra is not canonical. Now there's something else that could be replaced with the degree, but we won't talk about that just here. Maybe we'll do a follow-up video. So notice that this object over here has something of a degree of 2 plus 1 plus 1 plus 1. In other words, its degree is 5. Now this term that we're ending up with on the left is also degree 5, whereas this term on the right had a little bit of simplification and is degree 4. And we lost a degree every time we did this commutation relation. And that's because we've got this relation that allows us to write EH minus HE as minus 2E. So it's a quadratic combination of things rewritten as a linear combination of things. Meaning, like I said, this degree is not canonical. Now, one thing that I would like to point out, which is pointing towards something that is maintained, which is like the overall charge of this situation. So if we were to say that the F elements are negatively charged, the E elements are positively charged, and the H elements are 0 charge, and then add all of that up, then that sort of measurement is maintained. So notice here we would have a charge of 3 from our E's, 0 from this H, and then negative 1 from the F. So in the end, our charge would be 2, because 2 plus 1 minus 1. And now look, both of these down here also have a charge of 2 for the same sort of reason. Here we have 3 minus 1, and here we also have 3 minus 1. The H is not contributing. Okay, so like I said, I've got a bunch of other videos related to this kind of stuff that you might want to check out. One should be on the screen right now. And also maybe post in the comments if you're psyched about stuff like this. These are, kind of the most fun that I have making videos. And honestly, like what I feel like I can contribute most to, because they're not just like contest problems. So if you want to help me think about more videos like this, maybe post those in the comments as well. And that's a good place to stop.